Now that I'm on a roll, I can keep going. For example, your intuition was that V should be 0 just by symmetry. It is true if there is isotropy, discrete symmetry, any kind of symmetry where left and right are equally important. This is not going to be very interesting. I'll find out that all odd moments, third power, fifth power, they'll all vanish. And see what happens if I compute the next moment. According to this formula, for S itself, this is limit t goes to infinity, 1 over t logarithm of this integrated expectation value. So when you take a first derivative, and again, we believe this will have a nice limit. If it doesn't, then we are encountering something called anomalous diffusion, and they'll have a physical reason to. But the generic case will have nice limit. So what happens is logarithm puts this object down here, e to the b. And when I take a derivative of what's in the argument of the logarithm, I'll get xi times t weighted by this function, integrated over a whole space. And this is kind of nice because if the observable was just 1, this is normalized correctly. I said beta equal to 0, I get my formula. But writing it this way, because you want to see the general structure of this. If you go and compute the next derivative, there's a function s, parameter beta. I know that when beta equals 0, I don't have any interesting observable. This whole thing is 1. I know that logarithm goes through 0. So I know that this function looks something like that. And its value at 0 equals 0. Its first derivative has to do with average of my observable. And the second derivative will have to do with local curvature of some kind. I'll take this limit later. This is all true for any finite t. And then if I go upstairs, the only dependence is in beta, so I'll get xi from before. And now I'll bring xj. That's something bilinear in position at time t and its components. When I take derivative of this object, I get minus. Then I get whatever was downstairs squared. And from here I've inherited xi. And from taking derivative of that is exactly what I already did before. So I get xj. And this thing is squared. And now you see it's looking sensible. It's expectation value of 2 observables, whatever, integrated observables divided by the normalization when this is set equal to 1. And it's divided by the expectation value of the observable squared. So this is called cummulant expansion. And that's just the beginning of it. You can compute higher moments if you wish. But obviously, if you have an isotropic system, the first most important moment will be this one. There is an exercise to do which says cumulants are so cleverly done that if the distribution is Gaussian, exactly Gaussian, then this gives me the covariance matrix of the Gaussian, and all other ones are exactly 0. So it's designed to tell you how far are you from white noise or Gaussian behavior. So cumulant expansions are very smart, and they always show up, and they have all kinds of names. So this is called partition function. You're adding up all possible paths. And then this thing is called free energy. And I try to avoid using these words because when they were originally invented, they were very closely married to statistical physics, so bouncing little things, and Hamiltonian energy, losing energy. So they were really free energy, and then there's a Gibbs free energy. The thing is much more general and used in quantum field theory, in stochastic processing, and probability theory, and statistics, every place else, and they're just the natural thing. And in particular, if I look at second derivative, evaluate it at beta equal to 0, what I'll get when beta equals to 0, this is 1, this is 1, this is 1, 1, 1, 1, and I will get that this equals limit t goes to infinity 1 over t xit xij. So average value over whole space, how far I've gotten in time t, minus the expectation value of each one. So I can write it this way. And then there is just a little algebra for you to show that this is the same as saying this is the expectation value of xi minus where you think on average it should be, by estimating it by the drift, this mean velocity, times xj, where on average you think you should be by computing velocity for the j coefficient.